Hello everyone, I'm Professor Harrison and welcome back to our module on probability for finance. Today we're going to be covering expected value, what it is, how to calculate it, and a set of properties that make it one of the most useful tools in quantitative finance. We're following Danny, the gambler with a mountain of debt, working his way through a box of mysterious letters addressed to his late father, trying to understand what happened to the family fortune. Today he's trying to figure out whether his betting strategy across all the bets he makes on a given night is actually working in his favor or whether the numbers added up honestly tell a different story. He opens up another one of those mysterious letters. The most fundamental question you can ask about any uncertain outcome is, on average, what do I expect to get? That is what expected value answers. The expected value of a random variable x is a weighted average of all the possible outcomes that can occur. For a discrete random variable, you take each possible value, multiply it by its probability of occurring, and sum the results. For a continuous random variable, the sum becomes an integral, the same idea, just extended to the continuous case. Either way, you end up with a single number that represents the center of the distribution. One thing worth noting is that the expected value does not actually have to be a value that the variable can actually end up taking on. Flip a fair coin. You get $1 on heads and $0 on tails. The expected value is 50 cents. You will never actually receive 50 cents, but the expected value is 50 cents nonetheless. All the expected value is telling us is that on average you will receive 50 cents, not that that's something that you're going to be able to actually receive. So let's work through a more structured case. Consider a corporate bond where the issuer can end up in one of three states over the coming year. In the base scenario, which has a probability of 45%, the bond will have a 4% return. The company may end up doing better than the base case, however. We'll say that with a 30% probability, the company is going to do well and the bond will end up returning 8% instead. There's also a chance that the issuer ends up doing poorly, which we'll call the stress scenario. In this scenario, the issuer is going to default and the bond will have a negative 22% return. That happens the remaining 25% of the time. The expected return is the sum of each return multiplied by its probability. So, for example, in the strong case, we would multiply the 0.08 times 0.3. In the base case, we would multiply the 0.04 times 0.45. And in the stress case, we would multiply the negative 0.22 times the 0.25. We can then add all these together and get that the expected return is negative 1.3%. Notice what that number tells you and what it doesn't. It doesn't tell you what will actually happen in any given year. In any specific year, you either get 8%, 4%, or you get hit with a negative 22%. The expected value is a long run average, what you'd end up on average across many repetitions of the same uncertainty achieving. Expected value has a property that makes it extraordinarily useful for portfolio analysis called linearity. Linearity says the expected value of a sum is the sum of the expected values. This is true even if the variables involved are correlated, which is great for things like stock returns where correlations are commonplace. Linearity gives us two important properties. The first piece is that if you scale a random variable by a constant and then add another constant, the expected value scales the same way. So, for example, the expected value of a times x plus b equals a times the expected value of x plus b. The second piece of linearity is what makes portfolio analysis tractable. The expected value of x plus the expected value of y when both are random variables is just the expected value of x plus the expected value of y. And this extends to any number of variables, making the math behind portfolios a whole lot easier. Here's what that means for a portfolio. Suppose you hold a portfolio with weights across n assets. The portfolio return is a weighted sum of individual asset returns. Because of linearity, the expected portfolio return is just the weighted sum of the individual expected returns. You weight each asset's expected return by its portfolio weight, add them up, and then you're done. It's as simple as that. Let's apply this. Suppose we're evaluating a portfolio with three bond positions. The first has a portfolio weight of 50% and an expected return of 3%. The second carries 30% weight and an expected return of 5%. The third is 20% weight with an expected return of 1.5%. By linearity, the expected portfolio return is 0.5 times 3% plus 0.3 times 5% plus 0.2 times 1.5%. That ends up giving us an expected portfolio return of 3.3%. The key thing about linearity is what it doesn't require. You didn't need to know whether these bond positions are correlated or if they move alongside one another. You didn't need a joint probability distribution over all three assets simultaneously. Linearity just works. The expected return of a portfolio is always a weighted average of the individual expected returns. That is one of the most used results in all of portfolio management. There is one important warning before we move on. Linearity works for sums, but not for nonlinear functions of the random variable. The expected value of a function of x is not, in general, the same as applying that function to the expected value of x. We actually already saw this. The expected value of x squared is not the same as squaring the expected value of x. Those are different numbers, and variance, which we will cover next, is built entirely on that gap. Anytime you're working with a function that isn't just addition and scaling, you cannot push the expected value through it directly. Danny puts down the letter. He's been thinking about whether any given bet is worth making. Does the parlay pay off? Does this poker session end up positive? But linearity says something more direct than that. He doesn't need to figure out the joint probability of every combination of outcomes across a full evening. He just needs to figure out the expected value of each of his individual bets. He goes through the bets he makes on a typical night, the sports parlay, the poker session, a few prop bets. He knows enough about the odds to put rough numbers on each one. Each one individually has a negative expected value. And by linearity, the expected value of the full evening is just the sum of those individual expected values. Each of those negative numbers, he adds them up. The total expected loss per night is a number he finds uncomfortable to look at directly. He has been treating the occasional big win as evidence that his approach works, but the expected value doesn't care which nights you remember, it weights everything. So that's expected value. It's a weighted average of all possible outcomes where the weights are the probabilities. And the linearity property says that the expected value of a portfolio is always a weighted average of the individual expected returns, no matter how those assets relate to each other. That's one of the most used results in all of portfolio theory. The key caveat is that linearity works for sums but breaks down for nonlinear functions, a distinction that keeps showing up every time we work with squared terms, products, or anything beyond simple addition. Expected value is the foundation everything else in this module will be built on.